The 2010 Jabulani World Cup football has been criticized by many goalkeepers due to a knuckling effect it tends to exhibit. The knuckling occurs when the ball is traveling at lower velocities, causing eddies and vortexes along the ball's path, causing it to move in unpredictable ways. The 2014 Brazuca World Cup ball is designed to address these problems. The new ball is designed to be rougher and with less panels to make the ball more accurate and travel further.
NASA turned the Brazuca soccer ball into an aerodynamics lesson by putting it into a wind tunnel and calculating the drag force. Here's a video of it.
Some way to say happy holidays. Aerodynamics basically is the study of fluid flow around objects. NASA is not in the business of designing soccer balls or any balls for that matter, or testing them. What we do use sports balls here, especially in our lab, is for educational purposes. We found that it's very easy to get young kids interested in our field by showing something they can relate to. What we have here is a wind tunnel, which is basically a chamber through which air flows. When it comes to soccer ball, what we're looking at is the flight of the ball through the air. There's a very thin film or layer that forms near the ball surface, and it's the behavior of that layer which we call a boundary layer, which is critical to the performance of the ball. As far as the aerodynamics go, it's the structure of the outside of the material, the roughness, that's what determines the aerodynamics of the ball. Knuckling is when the ball flies erratically through the air, or it may change directions as it's flying through the air. What's been done to the Brazuca is that by using these panels with fingers on it, the seam length has been increased compared to the ball in 2010. What we're looking at with the smoke patterns is where does that smoke leave the ball, at what point along the surface. And when that position of that separation location changes suddenly, then that is the speed at which the ball will knuckle the most. I think the basic message for the players is that I think you'll see less of this knuckling effect. They'll find that it behaves more like the traditional ball, and I believe they'll be happier.
Our observations are different soccer balls have different number of panels, and soccer balls also have different textures. The Brazuca and the Jabulani, Brazuca had the Brazuca had 6 panels, and it was rough compared to the Jabulani, which had 8 panels, and it was a lot smoother. So our hypothesis is the smoother the texture, the more knuckling it will have. And the second is a different number of panels affect the behavior of the ball in the air after kicking it.
In order to test our hypotheses on these two balls, we just found the graphs to the right, which the top one depicts the drag coefficient versus the Reynolds number of the Brazuca ball. And the black line indicates a smooth sphere at those Reynolds numbers as well. And the bottom graph shows the drag coefficient versus Reynolds number for the Jabulani ball. As you can see, the Brazuca ball experiences a sharp drop in the drag coefficient at higher Reynolds numbers once you get past about 200,000. The Jabulani does not experience this until about 350,000. So we then used these Reynolds numbers and the density of air as well as the viscosity of air and the diameter of the ball to find the velocity that each must be going to reach this lower drag coefficient. And these were calculated to be 13.38 meters per second for the Brazuca ball and 23.4 meters per second for the Jabulani ball. This indicates that the Brazuca ball can be traveling at much lower speeds compared to the Jabulani and still have stable flight and not be disrupted by the airflow around it, because it is protected by the turbulent boundary layer at higher velocities. Based off of this analysis of the velocities that the balls must be traveling for a lower drag, we came to the conclusion that the bazooka performs better because while above that velocity, it experiences low drag, and then once it does fall below that, the paneling on it, since it has longer seams, does not act as a rudder as the Jabalani ball does. So in combination, the Jabalani's higher speed required for low drag, once it falls below this, the seams for its panels act as rudders, and the random air movements over the ball's surface cause it to change direction, hence the knuckling effect. Then we decided to find the total distance that each of the balls would travel regarding them as projectiles, using some of the previous information calculated, such as the coefficient of friction, which is a function of Reynolds number, from the graphs as well. And we used this to find the terminal velocity, and then plugging all the information we know into these equations, you can get the total distance that each ball has traveled with an initial speed of 26.8 meters per second, which is the average velocity of a soccer ball kicked by a professional player. So the bazooka ball was then calculated to travel a distance of 35.4 meters, and the Jabalani of 30.8 meters. So in conclusion, the bazooka ball, the dimples have a larger effect on the total distance it can travel without being affected by random air motion because of the turbulent boundary layer that protects it, keeping it at a lower coefficient of drag. And the panels don't catch the random air when it does slow down and is affected by drag more. So overall, it makes it a much better ball at range and at closer distances. And the Jabalani performs worse in these aspects.